right, welcome back from spring break. Hope you all enjoyed your time off. It's good to see everyone. Before I start class, I'm going to have a quick announcement about they had this last time, so if any of you went, you'll remember that there's a NSM student leadership does study nights for some of the core courses, and with our exam coming up 1 week from yesterday is when it starts. This Thursday, March 20th, in this very room, 5:45 in the evening, they'll have that session. I don't know the details about what they do there, but it's never hurts to get more exposure and review things as you prepare for an exam. All right, so what we're going to continue on with today are more things related to the topics of Chapter 6. Remember, Chapter 6 covers chemical reactions that happen in aqueous solution. We had already sort of gone through two major classes, which is acid, base, and precipitation. And then we're going to cover the third major class today, which is redox reactions. Just to sort of also remember that if we have to do this, I always forget because it's Tuesday. This is the analysis here is probably not perfect anymore because we did change the grading scale in terms of the weighting of the exams and also like the actual grade cutoffs. So there's not like this is not a perfect analysis anymore because this is data from a few years ago when things were a little bit different. But I think the trend is still likely going to be true. So there's there's always a lot of students that want to do better on the second exam than the first. I'm sure most of you aren't hoping to do worse. And so the question is, how often does that happen? And sort of what does your performance on exam one kind of project in terms of your final grade? Now, these are all averages. So as anybody who's taken statistics knows, averages just sort of tell you the sort of middle ground. There's always going to be outliers in either direction. So just because you didn't do well on the first exam doesn't mean you won't on the second exam, but there's some statistics that kind of point to really with the situation. So the cutoff that I used for this analysis was 55% on exam one, which is roughly the cutoff now between a C- and a D+. For most degree plans, you need a C- to consider the class as passing. So that's sort of the target. That's also the grade that the university cares about in terms of student success metrics. So in that semester, which again, this was about 5 or 6 years ago now, but we haven't changed the course too much. For students that scored 55% or below on exam one, obviously they want to do better in most cases. Only 26% of those did improve. 61% had a worse score on the second exam than the first, even though and then about 13% stayed the same. So the most likely outcome, again, not the only outcome, as you can see, 26% did get better, but the most likely outcome is not to improve. And then in terms of what that means for their final grade, now a lot of students who were in this category, 55% or below on exams 1 and 2, they drop a class, they kind of fall out of the picture. But for those that decided to stick it out and finish the course, none of them got a B- or better. Again, that might be a little bit different now because the grading scale is a little bit easier than it was back then. But still, it's not likely that you're going to get up to a B if you're doing that poorly on the exams. And then, only about 12% of those got even to that C- range. And the vast majority of people who were below 55% on the first two exams ended up with a D or below. So that's kind of just, again, a picture of what usually happens. There's outliers to all of this and probably a little bit of differences now because of the change in grading scale. But it means that if you're sort of in a situation where, you weren't too thrilled with how you went on the first exam, especially if you're kind of in that borderline range between C and D, you need to get up into the passing range. You need to take the second exam very seriously, obviously. And if it doesn't go better for you, you shouldn't take that as like a personal fault. That's just what happens in most cases. So it's not, something to be ashamed about. But at the same time, it means that you should seriously consider whether you want to keep pushing forward in the course to try to have the unlikely outcome of getting to where you need to be, or if dropping the course is better for you, which is often the case. So we can certainly have this conversation. So it's not intended to scare anyone, but it's just to show that really after the first two exams, especially, like there's not usually a lot of movement in the grades. You can go up maybe one, down, drop one, and there's still a lot of points, so it's still possible to improve a lot. But in terms of the regular happenings and the regular occurrences, most likely you're going to be where you kind of are now, or drop off a little bit. Okay, so that's just a little bit about some statistics from previous years that I think are still relevant today, even though there are some changes. All right, we're gonna do a quick review of some of the things that we covered last time. Um, just to reorient yourself. So as I mentioned at the start of this, there's three major categories of chemical reactions that occur in aqueous solutions. We've covered two of those so far. So the first one we did was precipitation reactions, and these ones are typically pretty easy to identify because the reactants and products are all ionic compounds. Two ionic compounds react, and they form two other ionic compounds as products. And if it's a precipitation reaction, one of those products, or both in some cases, would need to be insoluble in water, thus falling out of solution as a solid. So typically what we ask you to do in these types of in this type of analysis would be to write the chemical equation and then predict what, if anything, will precipitate. So we have here sodium phosphate and calcium chloride as the two reactants. So we need to convert names and formulas between each other. So we need to get the formulas of these compounds. So phosphate is PO4 3 minus. Sodium is in the first column of the periodic table over there, Na. And so it's going to be a +1 cation. So the correct formula for sodium phosphate is Na3PO4. I went quickly through that, but those are things you need to refresh on definitely for this exam because we talked about ionic compounds a lot in chapter 6. And then it's going to react with calcium chloride. So calcium is one column over from sodium, Ca. So it's going to form a 2+ cation. Chloride is in the second to last column of the periodic table, Cl. So it'd be a -1 anion. So calcium chloride would be CaCl2. So those are the two reactants that we have. Now then recall what we're going to end up doing here on the product side is we're going to swap cations and anions from the two reactants. So the cation from the first reactant, which is sodium, is going to pair up with the anion from the second reactant, chloride, and make one of our products, which is NaCl, to sodium chloride, simple formula. And then we're also going to make calcium phosphate. So calcium 2+ with the phosphate anion. This formula is a little bit trickier because it's Ca2+ PO4 3 minus. So if we want to make a balanced ionic compound with that, we need subscripts on both of them. So it's going to end up being Ca3 and then PO4 2 is the formula for calcium phosphate. And then from there, we need coefficients to balance things. This typically would be pretty small coefficients for these types of reactions. So we have 3 sodium, and I like to balance just one ion at a time. That's usually the way to go. So we have 3 sodiums here on the reactant side, Na3PO4. So we need a coefficient of 3 there to balance. Remember, we don't want to start adding subscripts. That's going to change the whole formula, change the charges of everything. We add coefficients now to make sure everything's balanced. So then we have, but we probably jumped the gun a little bit because what we also noticed is that we have 2 phosphates on the product side. So we need to have actually a coefficient of 2 there to have 2 phosphates on both sides. That means we now have 6 sodium. So we actually have changed that to 6. So sometimes you have to guess and check a little bit. This is about as complicated as it gets for precipitation reactions. And then we have 6 chlorides and 3 calcium. So to balance that, we need a 3 there. So those are about the largest coefficients you'll ever see in a precipitation reaction, but we did need them to balance. So that's the balanced equation. We do need to then also add the little markers here to indicate which, if any of these, is going to be soluble or insoluble. So if you remember the solubility rules, all sodium salts, anything with Na plus in the formula, any ionic compound is going to be soluble. So that one's going to remain aqueous. So sodium and chloride would be our spectator ions. But here for calcium phosphate, almost all phosphate salts are insoluble unless they're paired with something like lithium, sodium, potassium, one of those special cations. So this is going to be our precipitate here, a little S next to it, and that's going to be the one that we'd identify as the precipitate. Remember, the precipitate is the substance that's insoluble in water and would then form as a solid in the reaction. All right, so any questions on precipitation reactions that you want to clear up real quick before we move on? All right, and then the other major category we did was acid-base reactions. So again, these are usually pretty easy to identify because the two reactants, one's an acid, one's a base. Typically, the base is also an ionic compound, but then the other reactant in this case would be a covalent compound that functions as an acid. So we have here the reaction of sulfuric acid and lithium hydroxide. How many moles of water are formed when the reaction is balanced with the smallest possible whole number coefficients? So very similar to the last one, we need to write out the reactants, predict the products, and then put in some coefficients to balance everything. So sulfuric acid is the acid that comes from the sulfate anion, SO4 2 minus. So it needs two H's in the front, H plus in the front to balance that and make the acid, which is H2SO4 for sulfuric acid. So when you're constructing the formulas of acids, you just need to know the formula in charge of the anion, and then you add however many H pluses, hydrogens in the front to balance that charge. So H2SO4 is sulfuric acid, and the base that we're reacting with is lithium hydroxide. The vast majority of acid-base things we deal with in this course would use hydroxide bases, so just ionic compounds that have OH minus as the anion. Lithium is also in the first column right above sodium, so it's a +1 cation. Hydroxide is always OH minus, so you just need a 1-to-1 ionic compound to have that charge be balanced, so LiOH. Now, in some sense, the way that an acid-base reaction works is similar to the way that a precipitation reaction works. We have ions from reactants and products that sort of swap with each other. The only difference here, though, is that from the acid, the ion is formally H plus, and that's going to combine with OH minus to make water. So whenever you have an acid-base reaction, the H plus from the acid combines with OH minus, not to make an ionic compound in this case, but to make water, H2O. So you're going to make H2O as one product, which you can typically indicate as L for liquid. And then the other product is just going to be the ionic compound that forms from the ions that are left over. We have SO4 2 minus from the acid, Li plus from the base. So you need two of those Li pluses to balance the charge, Li2SO4. And all lithium salts are soluble, so we can put a little AQ next to that. It's kind of sloppy, but you can get the idea. Now, the most important aspect of this question is to balance the equation and figure out what's the coefficient in front of water. And there's usually a pretty easy way to do that, which is you look at how many H pluses your acid has. So H2SO4 has two H pluses in the formula. You look at how many hydroxide OH minuses are in the base. This one only has one. It's just LiOH with just one hydroxide. And so every time you have this situation, you need the same number of H plus and OH minus to react with each other to make water. And then however many you have is going to be the number of molecules of water you form. So we have two H pluses. That means we need two OH minuses. So we need a coefficient of 2 here. And so then now when they react with each other, you have two H pluses, two OH minuses. You're going to make 2 moles of water. That's really what this question was asking. And that would be the only coefficients you would need to balance this. A 2 in front of there to make sure you have the same number of OH minus and H plus to react with each other. And when you have 2 OH pluses, 2 OH minuses, 2 H2O will form. Okay? So every acid-base reaction has the similar pattern. Acid plus base makes water plus ionic compound. And then you just sometimes need some small coefficients to make sure everything is balanced. So you're going to make 2 moles of water in this case is what the question was asking. All right, any questions on acid-base reactions before we move on to what we're doing for new today? All right, we still have our interior thunderstorm going on, it seems. So sorry about that. So obnoxious. All right, so then what we're going to move on to is the last major category, which is redox reactions. Now, the reality of the situation is that anything that's not a precipitation or acid-base reaction has to be a redox reaction, but sometimes it's not so easy to just look at things like that. So we are going to sort of go over a formality that we use to help us identify whether something is a redox reaction, and then balance it. It's also going to help with that as well, because sometimes balancing redox equations is a little bit trickier than we saw for precipitation and acid-base. Now let's go over some of the key terminology first. So we call them redox reactions because they really involve two things happening at the same time. And these two can't occur without each other. So one is called oxidation, one is called reduction. So oxidation involves loss of electrons. So in a redox reaction, typically one of your reactants will lose electrons. Now, those electrons can't just vanish into space. They have to go somewhere, so they're going to be taken in by one of the other reactants. So the reduction part of this is one of the reactants is going to end up gaining electrons. So the combination of these two things together is what we call a redox reaction. And it's going to be a reaction that involves transfer of electrons. One thing's going to lose electrons. That's going to be the thing that gets oxidized. And then the other thing is going to pick up those electrons. That's going to be the thing that gets reduced. Now, there are some redox reactions that you'd be familiar with in your everyday life, whether you realize it or not. So whenever a metal like iron rusts, or sometimes copper also forms copper oxide, which is that green coating you'll see on copper things, that's a redox reaction. That's where oxygen is gaining electrons, and the metal is losing electrons, and you form rust. Anytime you burn something, that's a redox reaction. The major focus of this chapter, keeping with the theme of chapter 6, is going to be redox reactions that happen in aqueous solution. But some of them are things you're familiar with. Now, there is a good way to remember which one of these is oxidation, which one's reduction. So if you just remember, so Leo is a lion. Leo is the Latin word for lion, as it turns out. And Leo says gur. And so that helps you remember that if you lose electrons, that's going to be, I'll write it vertically. I think somebody on Teams is not muted right now. Would that be possible to fix? I don't want to look at who it is and call you out by name, but if you realize you're not muted, please. Thank you. All right, so then we have lose electrons is oxidation, Leo, and then the lion, Leo says gur, which is gain electrons, is reduction. So that's how I always remember which one was which. But as I said, they always happen together. You're in a redox reaction, both things are going to be simultaneously occurring. One reactant is going to gain electrons, one's going to lose electrons. Now, the way that we're going to go about sort of identifying if it's a redox reaction to begin with, and then it's also going to be an important tool for us to help us balance redox reactions, is a formality called oxidation number. So what we're going to basically do in a redox reaction is every element, every atom that's in that equation, we're going to assign an oxidation number to it. And that's sort of just an accounting trick we use in chemistry to figure out if something is gaining or losing electrons. That's all it really is. So we have a series of rules then that we need to remember to understand how to assign oxidation numbers. Now, there's some relation of this to something we learned earlier. If you remember in chapter 3, we talked about formal charges in the context of drawing Lewis structures. This is sort of a similar approach, but there is a key difference. So in formal charge, we sort of divide the electrons evenly. We assume all the bonds are covalent, and when we calculate a formal charge, we assume that any covalent bond is perfectly shared between the two atoms. When we're assigning oxidation numbers, we treat every bond as ionic, and we give all of the electrons to the more electronegative atom. And only oxidation numbers, not formal charges, only oxidation numbers can tell us whether something is being oxidized or reduced. If something is being oxidized or reduced, its oxidation number will change between the reactant and the product side. And so that's how we can decide then whether it's being oxidized or reduced and how many electrons are then involved in that process. But first, we have to understand how to just assign oxidation numbers. All right, so the way it works is there's a series of rules. Some of them are very obvious. Some of them you have to think a little bit more about. So it looks like a lot, but most of these things you don't have to think too hard. Just like we saw with formal charges, another similarity between oxidation number and formal charges is that in any compound, the sum of the oxidation numbers in that compound equals the overall charge. So if it's a neutral compound, all the oxidation numbers have to add up to 0. If it's an ion by itself, a lot of redox reactions are written as ionic equations. The sum of the oxidation numbers will equal the overall charge on that ion. So for every reactant and product, that has to be true. So when you're assigning oxidation numbers, what this means is that you can check yourself to make sure this is true. And some oxidation numbers we will assign by difference. We'll have some atoms in the compound where the oxidation number is obvious, and then by difference, using this rule here, we'll assign the other one that we don't know. All right. Now, there's going to be some when you're looking at redox equations and trying to balance them, which is the main thing you'll be doing in this part of the course. There's going to be some oxidation numbers that are very obvious. So, as I said, a lot of these are written as ionic equations, and if you just have a monoatomic ion in solution, Na plus, Fe2 plus, Cl minus, just an ion by itself in solution with a charge associated with it, the oxidation number is equal to the charge. So for those ones, there's no thought involved. The charge will be given to you, or you'll be able to predict it from the periodic table if it's one of those where that's easily done. So if it's a monoatomic ion, which is just a single atom with a charge on it, the oxidation number is equal to whatever that charge is. So those are easy to assign. The other ones that are pretty easy to assign, because we pretty much already learned how to do this, is if you have an ionic compound, we already know in ionic compounds you typically have a metal cation and then some non-metal or polyatomic anion. But in an ionic compound, the metal's oxidation number is equal to its charge. So in ionic compounds, they'll always have positive oxidation numbers. Oxidation numbers can be positive or negative, and it's going to equal the charge of that metal ion in the formula. All right, so we learned way back again in chapter 3 how to predict charges of ions that are involved in ionic compounds. For the metal, the oxidation number is just equal to that charge. So nothing new that you need. I didn't number these correctly. Can't count today. Still on spring break. All right. Yeah. 3, if you have an ionic compound, there's going to be some charge associated with the metal, which you either can predict from the periodic table if it's the main group metal, or you use the charge of the anion to back out what the charge of the metal is. And in that case, the oxidation number of the metal is equal to its charge. So for ionic compounds, that's going to be the case. Another one that is fairly easy to deal with is if you have a neutral element. So if you just have, iron by itself, Fe, or you have a diatomic element like N2 or O2. If it's a neutral element, so there's whether it's monatomic or polyatomic, but just no charge associated with it, the oxidation number is equal to 0. And that's going to be the only time you have, at least in our course, an oxidation number equal to 0. So if you have an element as one of your reactants or products, the oxidation number for that atom or both of those atoms, if it's diatomic, is going to be 0. Now, that's also a helpful one to remember because, as we said, neutral elements are the only thing that have oxidation numbers of 0. We identify redox reactions in terms of whether or not oxidation numbers are changing between reactants and products. So if you have a neutral element in your equation, it has to be a redox reaction because the oxidation number has to be something different than 0 on the other side of the arrow. So if there's an element, it has to be a redox equation. So O2, N2, Fe, Na, if something like that, if just a plain old element is one of your reactants or products, that has to be a redox equation. All right, now we get to the ones that are, you have to remember a little bit and are not always obvious, but there's a few that are still pretty easy to deal with. So one of the elements that's easy to deal with when you're assigning oxidation numbers is hydrogen. Hydrogen only has 3 possible oxidation numbers. As we said, it's 0 if it's hydrogen by itself, H2. But if hydrogen is in a compound, it only has 2 possible oxidation numbers, +1 or -1. It's going to be +1 if it's bonded to a nonmetal. So any covalent compound that involves hydrogen, whether it's an acid or just a regular old covalent compound, the oxidation number for hydrogen in that compound, every hydrogen in that compound will be +1. The only time hydrogen is -1 is a situation we haven't really encountered probably yet. But if hydrogen is bonded to a metal, or a metalloid, primarily boron and silicon being the 2 common ones. We haven't really seen that yet. those are called metal hydride compounds where the hydrogen actually functions almost like an anion in that case. But that would be the only time when hydrogen has a -1 oxidation state, is when it's bonded to a metal. Well, it won't see it all the time, but it's something that might come up. Another one that's easy to deal with is fluorine. So remember we said when we're assigning oxidation numbers, we didn't really go through this in formal terms altogether, but when you're assigning oxidation numbers, you're giving all the electrons to the more electronegative element. That's where all these rules come from. Fluorine is the most electronegative element on the periodic table. So that means unless it's fluorine by itself, where the oxidation number would be 0 if it was F2, but if fluorine is in a compound, it's going to get all the electrons from that bond, and it's always going to have an oxidation number of -1. So if you see fluorine in any sort of compound, whether it's ionic or covalent, it'll have an oxidation number of -1. And then the other one that has a very typical oxidation number that you don't have to think too hard about in most cases is oxygen. Oxygen is the second most electronegative element on the periodic table. So if you give it 2 electrons from the bond, it's going to have a -2 charge. So the oxidation number for oxygen will be -2 in almost every situation, except if it's bonded to itself, if it's bonded to another oxygen atom, or if it's bonded to fluorine, which is not very common, but there would be compounds like OF2, where this rule, fluorine, the word always is doing a lot of work here. Fluorine would always be -1, and that means in that case, oxygen can now also be -2, because that would violate this first rule here. All right, but oxygen almost always -2 in the things you'll see. Like one common exception for this rule here, number 7, is hydrogen peroxide, H2O2. In that case, oxygen is bonded to itself, and so it would be a -1 oxidation number instead of -2, because the 2 hydrogens are +1, which means the 2 oxygens have to be -1 to all add up to 0. So we might see that sometimes, but mostly it's going to be -2. And then the last sort of rule here would be for the other halides besides fluorine. They're going to always be -1 unless they're the central atom in the compound or the ion. So things like the perchlorate anion, where chlorine is at the center, would not have this situation. Or if they're bonded to oxygen or fluorine, because those are more electronegative. So there are some exceptions to this, but especially in ionic compounds that involve halides, chloride, bromide, iodide, you would just assume the charge is -1, the oxidation state would also be -1. And that usually holds true. Now, there's a whole lot of elements that aren't covered in these 8 rules. So what do we do with those? Well, as I said, in many cases, we assign oxidation numbers by difference. You'll have all the elements in that compound following one of these rules here, except for one. And then that last one you'll get by difference using rule number 1, where the sum of the oxidation numbers equals the total charge. So a lot of times we'll do it by difference. We'll see examples of that later on. All right, so it sounds like a lot of rules to remember, but most of these things are things you already learned or are very easy to deal with. There's not a lot of thought that goes into them. And we're going to practice a lot of it today so you can see how this works. All right, so let's do some examples of just determining the oxidation numbers of each element in a compound. All right, so the first one here is sodium sulfate. Sorry, sodium sulfide is the correct name for that. So sodium sulfide is going to be the sodium cation. I'll open up the periodic table so you can look at it quickly. All right, so sodium, again, we've seen this already today, is here in group 1. So if it's making ionic compound with sulfur, we would predict that the sodium has a +1 charge as a cation. Sulfur here would gain 2 electrons to get to the noble gas configuration, so it should have a 2- charge as a stable anion. So just names and formulas of ionic compounds again. All right, so that's going to be the 2 ions that are involved. If we want to balance the charge and get the actual formula for the compound, we need 2 sodiums pluses to balance the 2- charge in sulfur. So it'd be Na2S. We didn't really need the formula of the compound here because we already determined the charges of the individual ion. And in any ionic compound, the charges of the ions will be equal to the oxidation state. So for this one here, there's not a lot of thought, additional thought that's needed because we have two elements in the compound. We're going to identify oxidation numbers for each of them. Sodium has a +1 charge, so its oxidation state will be +1. Sulfur as an anion has a 2- charge, so it would have a -2 oxidation number. So those are going to be the oxidation numbers for sodium and sulfur in that compound. And then if you want to verify that the first rule works, that the sum of the oxidation numbers equals the charge, sodium sulfide overall is a neutral compound, no net charge. So if we look at the sums of those, we have sodium, there's 2 in the formula. Each has a +1 charge. And then for sulfur, there's 1 in the formula with a -2 charge. And 2 minus 2 equals 0. So it's important to remember when you're assigning oxidation numbers, the oxidation number that you assign applies to every individual atom in that compound. So here we had 2 sodiums in the formula, so each sodium has a +1 oxidation number. So when we assign oxidation numbers, that's always going to be the case, where every individual atom has its own oxidation number. All right, any questions on that? So again, this was a relatively simple one. Ionic compounds, which we will see a lot, and we've dealt with a lot before. You just need the charges of the 2 ions, especially if it's a binary ionic compound. It's as simple as that. The charges of the 2 ions give you the oxidation numbers or oxidation states as well. All right, let's do a slightly more complicated one now. So here we have the oxidation numbers of each element in phosphoric acid. So for phosphoric acid, the anion associated with that is phosphate. I think we saw phosphoric acid earlier today. No, maybe not. But anyway, it's PO4 3- is the anion phosphate, which means the acid would need 3 hydrogens to balance the -3 charge. So H3PO4. Now, the one thing that I want to caution you about with acids is that I guess it doesn't matter too much in terms of how we assign oxidation numbers, but still, it's important to realize that when you write an acid formula like this, H3PO4, you always put the hydrogens out in front, and it kind of then suggests that the hydrogens are bonded to phosphorus. But in these oxy acids that have anions that involve oxygen, all the hydrogen atoms are going to be bonded to oxygen in that compound. It's not that important for this because either way, you would just assume that hydrogen is bonded to a non-metal anyway, but that is a key thing here. So for phosphoric acid, this is kind of secondary to the problem, but the Lewis structure would look like this. Where the 3 hydrogen atoms are all bonded to oxygen. And that's going to be true for any oxo acid. So if it's a anion with oxygen in the formula and you make an acid from that, whatever hydrogens you have are going to be bonded to the oxygen atoms. All right, so that's going to be not super important, but it is helpful in some situations to remember that. Now, the key thing here is when we're assigning oxidation numbers, we look for the obvious ones first. So hydrogen in any covalent compound, whether it's an acid or not, has a +1 oxidation number. So we can assign some of these pretty easily. Hydrogen is +1 because it's a covalent compound. Oxygen, again, drawing out the formula for this does help in that regard as well. In all of these oxoanions, oxygen's bonded to the center atom. There's no oxygen-oxygen bonds. So again, if oxygen is in a covalent compound and it's not bonded to itself, it has to be -2. So we can assign those 2 ones pretty easily, really just from the formula. It's a non-metal compound with hydrogen and oxygen, so you would typically assume +1 and -2 for that. There's very rare exceptions to that. None for hydrogen, and again, only if oxygen has a bond to itself. But this is one of those situations now where to get the oxidation number for phosphorus, we have to do it by difference. There is no set rule that we have in hand to determine the oxidation number of things in that whole column, really. Nitrogen, phosphorus, that whole column is one where they have pretty variable oxidation numbers, and it depends on what else is in the formula. So we're going to do that by difference. The sum of the oxidation numbers has to equal 0 because phosphoric acid is charge neutral overall. So 0 has to equal, we have 3 hydrogens in the formula that are each +1. We have 3 oxygens in the formula, 4 oxygens in the formula, O4, they're each -2. And then 1 phosphorus in the formula where we're trying to find his oxidation number. So we just have to do a little bit of algebra. We have -5 plus P equals 0, so we move the -5 over and find that phosphorus in this case has a +5 oxidation number, such that all of those add up to 0. So that's the one that we had to do at the end by difference. But again, if you see a covalent compound that involves hydrogen and oxygen, I mean, really, unless it's hydrogen peroxide, you would assume hydrogen +1, oxygen -2, done. Okay, so when, a lot of these problems involve assigning a lot of oxidation numbers. You don't want to spend 5 minutes on each one, so look for the obvious ones first. Hydrogen and oxygen are ones that are easy to start with. So we did that here. We had hydrogen and oxygen assigned right away, and then phosphorus by difference. So any questions on that? So you'll get good at doing this kind of math because it comes up a lot. Yeah, so it's basically just algebra at this point to get the oxidation number of phosphorus. Pretty simple algebra too. All right, and then the last one, which has some similarities, but this time it's just an anion by itself. It's not a full compound. The oxidation number is for the sulfate anion. So sulfate is SO4 2-. So again, we're going to follow a similar approach in this case, where we look for the obvious ones first. Oxygen bonded to a nonmetal. So if you see a polyatomic anion that involves oxygen, you can safely assume that the oxygen has a -2 oxidation number because it'll be bonded to the central atom and not to itself. So oxygen is -2, and then we're going to do the same thing as in the last one. We're going to determine the other oxidation number for sulfur by difference. But we have to remember here that we're not adding them up to equal 0 because this anion still has an overall charge of -2. So that's going to have to be the sum, not 0 in this case, because the sum of the oxidation numbers equals whatever the overall charge is. 0 if it's a neutral compound, but non-zero if it's an ion by itself. So what we have here is that we're going to set this all equal to -2, which is the total charge, not 0 in this case, and that's going to be equal to the oxidation numbers for oxygen. There's 4 in the formula. Each is -2, plus 1 sulfur in the formula with some oxidation number. So this is a -8. -8 plus what equals -2? It has to be +6. So similar approach, just this time we're setting equal to -2 because the overall charge is that. A helpful way also to check yourself, it's not a rule that you would follow, but it's a good check, is that the group number for a main group element is the maximum oxidation number you have. So sulfur, which we're dealing with here, is in group 6 of the periodic table. If we go back to the periodic table here, it's easier to see. So when we count the main group elements, we have 1, 2, 3, 4, 5, 6. Sulfur's in group 6, which means his oxidation number cannot be bigger than +6. And so if you ever get a number that's bigger than the group number, then you probably made a mistake, have made a mistake. So, phosphorus, which we saw in the last problem, cannot go bigger than +5. Sulfur can't go bigger than +6. Now they are variable, so they could be a number other than that, but they can't be any larger than that. So that's a helpful check as well. All right, I think that's the last one. We're just going to assign oxidation numbers, although we're going to have to do that many times later on when we balance equations. So this is what we're going to talk about now are the actual equations that we talked about for redox. So the terminology gets a little bit weird here. I understand. So we said at the beginning that oxidation means you're losing electrons, but the oxidizing agent is actually the one that gets reduced. This terminology always bothers me too, but there's nothing we can do about it because I don't rule the chemistry world yet, so I can't change it. But the reactant that gets reduced in a redox reaction is the oxidizing agent. Now, why do we call it an oxidizing agent if it's getting reduced? Remember, an agent is somebody that does something, an agent of change, for example, if you like that terminology. But the oxidizing agent is the one that does the oxidizing. It causes something else to get oxidized. Now, how do we identify what the oxidizing agent is? So we're doing it from the framework of the reactants. So whenever you're identifying an oxidizing agent in a chemical reaction, it's going to be one of the reactants. It's never on the product side. The oxidizing agent is the reactant that has its oxidation number decreasing during the reaction. So if you have an oxidation number decreasing from reactants to product side, whatever compound or ion that oxidation number is part of that's changing, that whole thing would be classified as the oxidizing agent. Okay. Then the reducing agent is the exact opposite. It's the reactant that gets oxidized during the reaction. I'll say redox reaction. I mean, these are the only types of reactions that have this anyway, but it's not like necessary. But in a redox reaction, we call it, again, for same reason, we call it the reducing agent because it's the one that does the reducing. It causes something else to get reduced, even though itself is being oxidized. And the reducing agent is the one where the oxidation number increases during the reaction. So very often, if you have a metal as one of your reactants, Fe by itself, Na by itself, zinc by itself, Zn, they'll have an oxidation number of 0 on the reactant side. In the product side, they'll be part of an ionic compound with a positive oxidation number. Their oxidation number is then increasing, and that identifies them as a reducing agent. All right, well, let's go through some examples of this and see like how we can use oxidation numbers to help us determine oxidizing agent, reducing agent, and some other things about it. All right, so we have this reaction here. We're taking PCl3, phosphorus trichloride, reacting it with O2 gas, and we're making a compound called phosphorus oxychloride. Now, is this a redox reaction or not? As I said, one helpful shortcut is if one of the reactants or products is an element, it has to be. So if you remember that I said that, and you remember it, a week from now when you're taking your exam, this has to be a redox reaction by that definition. But that's not always going to be true. You're not always going to have elements in your reaction, so you can't always use that shortcut. So let's go through the actual approach you would want to take in general terms. So what you have to do to identify if this redox reaction is you have to assign the oxidation numbers of every atom on the reactant and the product side. All right. So if we have PCl3 here, phosphorus is variable, but chlorine, if it's in a covalent compound and it's bonded to something less electronegative like phosphorus, will be -1. So we have 3 chlorines that are -1, which means phosphorus has to be +3 to balance. So we have a +3 for phosphorus, 3 -1 is for chlorine. Oxygen, as we said, O2 is an element by itself, charged neutral, so it's the only time we'll see an oxidation number of 0. And then when we go to this product here, POCl3, oxygen in a covalent compound, as we said, is -2. By the same argument as on the reactant side, chlorine is still -1, is still bonded to central atom phosphorus. And now we have to assign an oxidation number of phosphorus by difference again. So we have a -2, we have 3 -1s, that's equal to -5. That has to be then +5, such that all that adds up to 0. So I'm doing the algebra in my head now, but it's the same thing we covered earlier where we do that by difference. A -2, 3 -1s, those add up to -5. You need a +5 then, so that everything adds up to 0. So if we want to answer the simple question, is this a redox reaction? We see that phosphorus is changing from +3 to +5. +3 here on the reactant side, +5 on the product side. And there's always going to be a pair of things changing. It's not just going to be one thing. We also see that oxygen on the reactant side is 0, and it goes to -2 on the product side. So because we have changing oxidation numbers, you don't have to necessarily even find both of them. If you identify clearly that one oxidation number is changing, it has to be a redox reaction. So the answer to part A is yes, it's a redox reaction. Again, the shortcut that there's an element involved works here as well. So now we're also looking for is what is the oxidizing agent? The oxidizing agent, remember by the definition, the terminology is a little bit confusing, but it's going to be the reactant that gets reduced. And what that means is that it's the reactant where the oxidation number is decreasing, going down. Okay? So the one that's decreasing, phosphorus is increasing from +3 to +5. Oxygen is the one that's decreasing from 0 to -2. So in terms of oxidation numbers, as we said, oxygen goes from 0 to -2. And that means the whole thing that oxygen is part of as a reactant, so it's actually O2, that whole thing is going to be classified as the oxidizing agent. All right, because oxygen is having its oxidation number decrease during the reaction, and so whatever reactant oxygen is part of, which is O2 in this case, would be the oxidizing agent. So that's how we identify and answer those kinds of questions. We assign oxidation numbers for every atom on the reactants and product side. We look for which ones are changing, and if it's increasing or decreasing, that's going to tell us whether it's the reducing or the oxidizing agent. So then if we ask the other question here, phosphorus has its oxidation number increasing, so this whole thing, PCl3, would be then the reducing agent. Okay, so there's always one oxidizing agent, one reducing agent. Sometimes the same thing can be both the oxidizing and reducing agent. That's a weird situation, but you will always be able to identify those. All right, so any questions on this? All right, so then on to another one that's similar to this. Some of the same reactant, so the product for that one is not the reactant in this case. So we have here POCl3 reacting with water to make phosphoric acid and hydrochloric acid. So if you take this compound and dissolve it in water, that's what happens. It makes those two acids. So this one is not obviously an acid-base reaction. It involves acids. It has acids as products in this case, but it doesn't follow sort of the typical script for an acid-base reaction that we have. It's not acid plus base makes water plus ionic compound, but we also don't want to just assume that it's a redox reaction. So we have to go through the approach that we talked about last time, which is to assign oxidation numbers and then go through and figure out if they're changing or not. So this is the same one we had, so I'm not going to go through it again. We had +5, -2, and -1 for those three elements. We will see water all the time in redox reactions, so you should be able to assign the oxidation numbers of that in like 2 seconds after you've done it a few times. So as we said, in covalent compounds, hydrogen's +1, oxygen almost always -2. So +1 and -2 for water. Don't have to think about it after you've done it a few times. H3PO4. I think we did this one earlier also, but just to remind ourselves, we had +1 for hydrogen because it's in a covalent compound, -2 for oxygen in the vast majority of cases. So we had 4 -2s is -8, 3 +1s is +3, so -8 + 3 is -5. That left +5 for phosphorus. We did that one earlier, so if you want to check that in more detail, it is on an earlier slide. And then HCl, covalent compound involving hydrogen. So +1 for hydrogen, that means chloride has to be -1 to add up to 0. All right, so those are the oxidation numbers. And if we look what's happening here, we have 4 elements involved: phosphorus, oxygen, chlorine, and hydrogen. Phosphorus is +5 on the reactant side and is also +5 on the product side. Oxygen appears a few times, but on the reactant side, it's always -2, and on the product side, it's also -2. So there's no oxidation number for oxygen other than -2. Chlorine, -1 on the reactant side, also -1 on the product side. Hydrogen, these are all covalent compounds. It appears multiple times, but it's always going to be +1 for hydrogen. So in this reaction here, we see that none of the oxidation numbers are changing. Phosphorus is always +5, oxygen -2, chlorine -1, hydrogen +1. No differences between reactant and product side for any of the oxidation numbers. So because of that, then we can conclude that this is not a redox reaction. And you wouldn't be able to, we wouldn't expect you to identify this in a general chemistry course, but this one would be classified as an acid-base reaction. It's not obvious, it doesn't look like a typical acid-base reaction that we're used to, but it nonetheless is one, just a more complicated one. All right, any questions on that? Go ahead. The notes will be posted too, so if you don't have time to take photos, they'll be online after class. All right, so then the last thing we're gonna do, which is probably the most important. I don't know if this is still true because we did update our question banks for exams. I'll have to check it to see if it's still true. But many years ago, even before I started here, there was a former professor who's now retired who was in charge of like putting together all the test banks um, for the general chemistry courses. That job is now Professor Larson's, if any of you know him. But so a lot of things have still been retained over the years that we haven't changed things dramatically. But anyway, that previous person, he loved redox reactions. Like they were like near and dear to his heart. So there's always like overweighted test questions, in my opinion, on redox reactions. So I'll check if that's still true. It probably is, but you're going to expect on both the second midterm, which is coming up, and on the final exam, they're going to have at least probably in each case 2 redox reactions of balance if things have not dramatically changed since the last time I taught this course. So I have to check the question banks because I don't, go through them in detail all the time, but that was always the case. So we have to learn how to do this. And it is a little bit, it does take practice. Make sure you work on it. You have roughly a week or so to master this before the exam. But there's going to be a series of steps that we follow to balance oxidation redox reactions. In rare cases, you can just balance by inspection. We've learned how to balance chemical reactions back in chapter 5. You can just kind of add in the coefficients, make sure everything balances, and you're good to go. But sometimes they're a lot more complicated than we typically see. And on top of that, when you're balancing a redox reaction, if it involves charges in the reactants and products, so it's ions by itself, as they're often written, you have to make sure both the atoms and the charges are balanced. So you can't just balance the atoms, be like, okay, I'm done. Like, for example, if I can think of one, if you had this reaction here, you might be like, oh, well, that's easy to balance because and is it that easy? I hope not. No, it's not that easy. So you might be like, oh, this one's easy to balance. I just have 2 chlorines over here. I need 2 over here. Put a coefficient of 2. I'm done. But what you'll notice is on the reaction side, we have an overall +2 charge from iron +2. Here we have a +3 and 2 -1s, which adds up to +1. So the total charges are different on each side of the arrow. That would mean that we're basically creating an electron out of thin air in this reaction. So this is not the correct way to balance this because even though the atoms are balanced, the charges are not. So you're balancing a redox equation, atoms and charges have to be balanced. And a lot of times it's hard to do that by inspection, by just looking at it and guessing and checking. So we are going to learn a systematic approach for doing this. It takes time, it has a lot of steps, but it always works. So the first thing you want to do if you're balancing a redox reaction, we will always give you all the reactants and products. You just have to supply the coefficients, really. You don't have to write it out like we do for other types of reactions. But the first thing you're going to do then is you're going to assign all the oxidation numbers. Not really a huge shortcut around that. And that's you're going to have to do that for every atom in the reaction. There's every reactant, every product, every individual element on both sides. So again, look for the easy ones first. Some of them are a little bit trickier, but most of them. So in this problem here, let's go through the easy ones first. Ion by itself, the oxidation number equals the charge, Cl minus -1 oxidation number. Ion by itself, +1 charge, +1 oxidation number. Ion by itself, Mn3 plus, same oxidation number. And then water is another very easy one. As I said, we see it all the time. +1 for hydrogen if it's a covalent compound, -2 for oxygen. So we still have a couple of tricky ones to deal with, though, because we haven't gotten manganese over here and chlorine over here. These are oxoanions, so that the approach we take for those is to assume that oxygen is always -2 in polyatomic ions, which is always the case. And then we do the other one by difference. So the overall charge of this is -1. We have 4 -2s from the oxygen, that's -8. They have to add up to -1, so that means we need a +7 there. So 7 -8 equals -1, okay? And then ClO minus, a little bit easier because there's only 2 atoms in the formula this time. -2 for oxygen. They have to add up to be -1. So what -2 equals -1 plus 1. All right, so we did those by difference. Review that earlier if you need to check why that is. But those are all the oxidation numbers for every atom. So you have to get good at doing that. You have to practice it, but it follows everything that we've covered earlier today. The next thing you're going to do is you're going to determine the number of electrons that are lost and gained. or the oxidizing and reducing agent, which is basically for each chemical species that changes its oxidation number. So the way that I like to do this is to draw tie lines between the things that are the oxidation, where the oxidation numbers are changing. So if we look at everything we did up above, we see that manganese is going from +7 to +3. So that's one of the things that's changing. So this one's +7. I'm not going to write out all of them again, but we're going to look at the ones that are changing. And then in a different color, I'll do the other ones here. So we had chlorine over here was -1 on the reaction side, +1 on the product side. So this one's -1 and this one's +1. So those are going to be the oxidation numbers that are changing. So I draw little tie lines between them. Then what we have to do is figure out how many electrons are being lost or gained. It doesn't really matter if we classify whether it's lost or gained for the purposes of balancing, but we do that by just the difference in oxidation numbers. So manganese is going from +7 to +3. That's a difference of 4. So that means this is a 4-electron process. Okay? It's, in this case, gaining 4 electrons because the oxidation number is getting smaller by 4, but we don't really care if it's gain or loss as long as we can count how many there are when we're balancing something. And then for chlorine, it's going from -1 to +1. That's a difference of 2. So there's a 2-electron difference there. So this is going to be 2 electrons. And again, we don't, if we're identifying which one's being oxidized and reduced, we care a little bit about this one as being, this one is losing 2 electrons, this one is gaining 4 electrons, but the number is the important part for balancing. So when you're balancing a redox reaction, as we said, you cannot create or destroy electrons. So you have to make sure that these two numbers are the same, and right now they're not, right? This one in blue is a 4-electron process. This one in red is a 2-electron process. So the way we deal with that is we first add coefficients to make sure that we balance the number of electrons lost or gained. All right. So that's going to be, again, looking at these two here. That was a 2-electron process. This one here was 4 electrons. We did that on the last slide. We have to make sure those numbers end up being the same. So if this one's 2 and this one's 4, we have to double this one to make them the same. And so we do that by adding coefficients of 2 to both the reactant and the product. So now we have this 2-electron process happening twice. So it's a total of 4 electrons, which balances the number of electrons that are being gained by manganese. Once we set those coefficients, so I even sometimes just write in coefficients of 1 here. Once we balance the number of electrons by adding coefficients to do that, we don't want to change those anymore, because if we start changing coefficients on any of those 4 things, the number of electrons are going to be out of whack again. So once we set that, once we figure out how many electrons are involved, once we get them balanced with coefficients, we don't want to change those. But the rest of the coefficients we still might have to adjust, and that we have to just do by inspection. There's no methodology for this at this point other than just making sure everything else is balanced. Now, the nice thing is at this point, the number of electrons is already balanced, so we don't have to worry about charges when we balance by inspection. We just have to balance the number of atoms on each side. So we balance the rest by inspection. So we figured out that there was a coefficient of 2 there, coefficient of 1 there, coefficient of 2, and a coefficient of 1. That was set to make sure the number of electrons was the same, being lost and gained. The rest we do by inspection. So what we see here is on the reactant side, we have 4 oxygens from MnO4-. We only have 2 from this product here. We need 2 more, so we need a coefficient of 2 in front of water. And then by virtue of adding 2 in front of water, that now gives us 4 hydrogens. So this needs a 4 to make sure hydrogen's balanced. So typically there might be a couple things left over at the end, often water, often H+, where you have to just balance those to make sure the number of atoms on each side is the same. And that's going to be the final balanced form for this. So that's the approach we'll take. 4 steps. The first 3 involve looking at the oxidation numbers and figuring out how much they're changing. So as I said, a lot of this just requires a lot of practice. So I have, how many more do I have? Like 3 more for you guys, I think, and that'll close us out today. Plenty of time to do that. So let's go through a few practices, because we're also going to run into a couple of situations that are a little bit more complicated than what I just showed. It still follows the same approach, but you have to think about a couple other possibilities that can happen. So we have this one here. We have the dichromate anion I- and H+ as reactants, forming chromium 3 plus I2. There's an element by itself, so it has to be a redox reaction, and H2O. All right, so we have to assign oxidation numbers. This one here is about the hardest you'll come across, Cr2O72-. That's a lot going on there. Polyatomic anion, so oxygen is -2. The overall charge has to be -2 as well for the whole thing. 7 minus 2s is -14. That means we need +12 to make those add up correctly. So let's do that. I'll write this up. This one's more complicated. So -2 is the overall charge of the anion. We have 7 minus 2s from oxygen. Should what be +8? The charge? Close. But we have to, that would, just check your algebra real quick, because then it's going to be 2 chromiums with what charge? X is the charge for chromium. All right, so -2 plus 14 is 12. So I think you subtracted instead of added. So we move this over, -14 over here moves over, that -2 plus 14 is 12. We had 2 of those to add up to 12, so each one has to be +6. So the charge for that is +6. You were on the right track for that one. Just, I think, mess up the algebra a little bit. All right, so you have a +6 there. Now remember, that +6 is each chromium atom is +6. There's 2 of them in the formula. Each one is +6. If that's the situation, we assume they're both the same. There's no other way to do it. Some of the rest of them are easy, though, so we can go through some of the nice, easy ones. Like this is -1 because it's an ion by itself. This is +1 because it's an ion by itself. Ion by itself is +3. Neutral element, remember, that's the only time we have oxidation numbers of 0, is when the element is just neutral and by itself. And then water, our old friend water, +1 and -2. Now, the tricky thing about this one that sometimes comes into play is that if we look at the oxidation numbers that are changing, we have +6 for chromium going to +3. So that's one of the ones that's changing. That's easy to find. And then iodine is going from -1 to 0. But when we're counting electrons for these, it gets a little bit more difficult, because here we have 2 chromiums that are +6 forming a chromium +3. So what I like to do to handle, there's different ways of dealing with the situation. What I like to do in this case is recognize, well, okay, we have 2 chromiums over here. We need to have 2 chromiums over there, regardless of what the number of electrons is. So I'm going to put that 2 in right away. Now, what that means, though, is that even though each chromium is only changing by 3 electrons, it has to happen twice, because there's 2 chromiums here in this compound. There's the Cr2O72-. So each chromium +6 has to go to +3. So even though the change for each chromium is 3 electrons, it's happening twice. So overall, this is a 6-electron process, because it's 3 electrons for each chromium. And I like to put the coefficient of 2 in right away to remind myself that whatever these coefficients end up being, this one has to be 2 times that one to make sure that we have the right number of chromiums on each side. We might still change them, but this one has to be double that one to make sure the number of chromium atoms doesn't change. And then same thing for iodine in this case. I- -1 oxidation number going to I2, which has 0. Each iodine is just changing by 1 electron, -1 to 0, but it has to happen twice, because this has I2 as the formula. There's 2 iodines in there, each of them going to 0. So similar story here. We're going to put a 2 there to remind ourselves that whatever the coefficient here has to be 2 times the coefficient here. And it's a 1 electron process for each iodine, but there's 2 iodines in the products, that has to happen twice. So in total, this is 2 electrons. Same argument as the first one. So now what we have is a 2-electron process and a 6-electron process. Those have to be balanced out now. So 2 times 3 equals 6. So we're going to have to further triple these coefficients to get the number of electrons the same. So this, instead of a 2, becomes a 6. Actually, let me write that out as a separate step, so you don't have to erase things. All right, so then what we do then is recognize that that has to be tripled to get everything equal to 6 electrons. So we're going to have Cr2O72-. that 2 becomes a 6 because we had to triple it to make sure it was a 6-electron process. We'll do H plus later on, but so I need a coefficient there eventually. And then again, we keep that coefficient of 2 because there has to be 2 chromiums to balance the number of chromium atoms on each side. That coefficient was a 1. We had to triple it, so it becomes a 3. Then we have water to do at the end. All right, so now we're just left. Again, these coefficients are now going to be set. If you want to write in a coefficient of 1 here, go ahead. Just to remind yourself of that. So this, and this are all set now to make sure that we have the same number of electrons being transferred between the reactants. But we have to still do H plus in water, and we just do that by inspection. So on the reactant side, we have 7 oxygens from Cr2O7 2 minus. So we need 7 waters to have the same number of oxygen atoms. The 7 in front of water leads us to having 14 hydrogens. So we need a 14 in front of H plus. So this one ends up being those coefficients. And again, this is one that would not be easy to balance by inspection because there's charges on each side, and you don't end up using the smallest whole numbers for each one. You have to use those coefficients to make sure that both the charges and the number of atoms end up being balanced. All right, any questions on that? Yeah. So the reason I did that in this case, you don't always do it that way, but is because for the chromium, its oxidation number is changing, and it only appears once on the reactants and product side. So I did that just to remind myself that like whatever this coefficient ends up being, it has to be 2 times that coefficient because there's 2 chromiums in this reactant, only 1 in the product. So I put those in. There's different ways of handling that, but sometimes if you don't do that, you'll accidentally put the same coefficient for both of these. You know, you might say like, oh, well, actually, they don't need coefficients because there's already 6 electrons. But then if you forget to put a coefficient there, you'll either miscount the number of electrons or you'll have the wrong number of chromiums on each side, or some combination of those 2 things will happen. So whenever you have that situation where the one that's changing oxidation numbers appears more than once on either the reactant or the product side, sometimes it's helpful to put some coefficients in initially just to make sure you count the electrons correctly and that you don't forget that the coefficients have to be different for those 2 things. Because in the previous example we did, because we didn't have that situation, the compounds where the oxidation numbers are changing end up having the same coefficient on each side. And that's usually the case unless you have it appearing more than once on one of the sides of the arrows. So that's why this is a 2 and a 2, this is a 1 and a 1. In that case, they have to be exactly the same as each other. But here we remind ourselves that that one has to be double, and same for iodine as well. All right. That won't come up all the time, but I want to make sure you see all the different possibilities. Yeah. Yeah, the reason we did that is after we finished counting electrons, this was a 6-electron process here. This one was 2 electrons. The number of electrons for both has to end up being the same. Okay, so to make a 2 into a 6, you have to basically find the least common multiple of 2 and 6 is 6. So you have to multiply this one by 3 to get to that. Okay. So that's the key step in every case where you have to make sure the number of electrons for the reduction, which is this one here, and the oxidation, which is this one here, the number of electrons has to be the same. All right, this one's going to have that same situation where we have nitrogen appearing once on the reactant side, twice on the product side. So it's similar story here. All right, so what we're going to do for this one is assign oxidation numbers, KiO4. It's an ionic compound. This is called a periodate anion, not very common one, but it's a potassium is +1 when it makes ionic compounds. It's right here in the first column. So we can assume that the charge of the ion and the oxidation state are both +1. Oxygen in polyatomic ions is -2. Then we just have to do the rest by difference, iodine here. 4 minus 2s is -8, +1 is -7. This needs to be +7, so if they all add up to 0. That's a charge-neutral ionic compound. NH3 is not too bad because it's a covalent compound with hydrogen, so those all have to be +1. 3 +1s for hydrogen is +3, -3 for nitrogen, so they add up to 0. Ki is a simple binary ionic compound, so it's +1 for potassium. Based on charge balancing or based on the location of iodine in the periodic table, that would have to be a -1 anion. So you're going to have a -1 oxidation number for that. Nitrogen is a neutral element, so it's the only time we'll see oxidation numbers of 0, and then +1, -2 for oxygen. So the first one was the most difficult, got easier after that. Those are all the oxidation numbers. So the ones that are changing are iodine, which is going from +7 to -1, and nitrogen, which is going from -3 to 0. Just like the previous example, this is a situation where nitrogen's oxidation number is changing, but it appears once on the reactant side, but there's two nitrogens in that product that are changing oxidation number. So again, we can help ourselves a little bit by putting a 2 there. And then when we want to count the number of electrons, we go by difference in oxidation number. Iodine is going from +7 to -1. So +7 minus -1 is a difference of 8 electrons. And then here for nitrogen, we have each one is a difference of 3. Nitrogen is going from -3 to 0. That's 3 electrons, but it has to happen twice because there's 2 nitrogens in the product that are both have 0 oxidation numbers. So overall, this would be 6 electrons. 3 for each nitrogen, but it's happening twice to make N2 as the product. Now we have to balance a 6 and an 8. So what coefficients can we use to do that? So we have to remember math that you probably learned like back in middle school. Least common multiples, I think, is the correct term for that. It's been a while. So 8 and 6, well, if we double 8, that's 16, but that's not a multiple of 6. But if we triple 8, that gets us to 24. So 24 should be the least common multiple of 6 and 8. So you would triple 8 to make it 24 electrons, and you would multiply that by 4 to make it 24 electrons. And I don't think there's a smaller number that works than that, okay? So this one was kind of a lot. So then we had to triple that coefficient. Those are the coefficients on KO4 and KI. So we triple those coefficients. I'll write it out again so we don't have to erase things we've already done. So we tripled that coefficient to make sure that it was 24 electrons. We tripled that on the product side as well. All right, and then what we have to go through is look at nitrogen now. So nitrogen, we had to quadruple the coefficients to make it up to 24 electrons. It was a 6 electron process as originally written. It needs to happen 4 times to make it a 24 electron process. So that means each of these two coefficients, NH3 and N2, has to get quadrupled. So instead of a 2, that becomes an 8. Instead of a 1, that becomes a 4. And that still makes sure then that we have the same number of nitrogen on each side. There's a total of 24 electrons. All that's left is water. So we have 12 oxygens here on the reactant side, 4 from KO4, 3 is the coefficient, so a total of 12. 12 waters will balance that. Let's make sure hydrogen is balanced as well. 12 times 2 is 24. 8 times 3 is 24. So I don't like the term killing 2 birds with 1 stone because I don't like killing birds, but nonetheless, that's what we did here. So we were able to balance both hydrogen and oxygen by throwing a coefficient of 12 in front of water. All right, questions on that one? So they get a little bit complicated, but I promise if you practice them, you'll start to learn how to do this. All right, the last one and the hardest one here. I know I'm driving you guys crazy with all these difficult ones, but I wanted to make sure that I showed you all the little tricky things that can happen. Many are much simpler than this. Many are more straightforward like we started with, but I want to make sure you don't see anything on your assignments that you're unprepared for. Okay, so this one here we have zinc plus nitric acid making zinc nitrate, NO, which is nitrous oxide, and water. Oxidation numbers are not too bad here. Zinc is an element by itself, so it's 0. I think we might have done HNO3 earlier, but if not, it's similar to some of the other ones we've done. Covalent compounds, so oxygen is -2, hydrogen's +1, and then we'll do nitrogen by difference. 3 minus 2s is -6, +1 makes it -5. We need a +5 so that they all add up to 0. Now, this product is a little bit tricky unless we remember also that it's an ionic compound. So if it's written as an ionic compound, we can use the charges of the ions to help us determine oxidation numbers rather than doing everything sort of algebraically. So in this compound, we have 2 nitrate anions. Each one's -1. So that means we have a -2 charge from the anions, which means zinc has to be +2. It's not the one that you may always remember, but zinc is always +2 when it makes ionic compounds. That's one of the ones that's invariable. Now for nitrate, we can either do the whole process again, or we can recognize that we have a nitrate anion here as part of our acid, a nitrate anion in the product, but still staying as a nitrate anion is not going to change its oxidation numbers. So this would still be -2 and +5, just like it was on the reactant side, because it's still a nitrate anion. This is a nitrate anion also, just has H in front of it instead of a zinc cation. So, or you can go through the whole process again for nitrate. It's NO3 minus. So you would need 3 -2s for oxygen. They have to add up to -1 is the overall charge, so this equals +5. -6 + 5 is -1. So either way, you get to a +5 for nitrogen on that one. NO is pretty simple because it's a covalent compound, so oxygen is -2. To make them add up to 0, nitrogen has to also be +2. And then hello water again, +1 -2. All right. So the situation that we run into here is if we look at the changing oxidation numbers, we find pretty easily that zinc is going from 0 to +2. So that's very straightforwardly a 2-electron process. But then what we also see is nitrogen here is the one that's a little bit weird in this case. Nitrogen's +5 on the reactant side. Now, if we look at the product side, there is some nitrogen that's still +5. That's part of the nitrate here. And there's nitrogen that's +2, which is having its oxidation number changed. So that one is changing by 3 electrons because it's going from +5 to +2. But we also have some nitrogen that's staying the same as +5. So how do we deal with that? Because we basically have two different things happening with nitrogen. It's being reduced from +5 to +2, but some of it is just losing its H+, making the nitrate anion and forming this ionic compound here. Again, you might have different ways of dealing with this, but what I like to do in this situation is we recognize now that some of the nitrogen in this equation does not change its oxidation number. So the tricky situation is that if we try to use the number of electrons here to balance this one here, we're still gonna have to add more to make sure that we have all the nitrogen accounted for in this product. It gets a little bit hairy. So the way that I deal with this is I'll actually separate it into two piles that we're going to balance separately. It's going to look weird when we first write it, but at the end we'll simplify it, but it makes it easier to balance in my opinion. Because the way that we balance redox equations is we use the number of electrons to balance the things where the oxidation numbers are changing, and then we just do everything else at the end by inspection. So we're going to balance some of the HNO3 using the number of electrons that are involved, and then we're going to balance the rest at the end just by inspection. So what we found was that this here was a 2-electron process. This nitrogen, which is +5, going to this nitrogen, which is +2, is a 3-electron process. So just like we always do, we're going to start by balancing those. This is a 2, this is a 3. The least common multiple is 6, so we're going to triple that, putting coefficients of 3 there and there. And we're going to double that to make them both equal to 6 electrons. So we're going to put a coefficient of 2 there and there. Now, at this point, we don't change those coefficients, but then we have to balance the rest by inspection. So we have 3 zincs, 2 HNO3. Those are balanced. Another pile of HNO3 that we have to balance to get the number of atoms the same. And then 3 zinc nitrates, 2 NOs, and water. So to balance by inspection, what we see is that we have 6 more nitrogens on the product side. Zinc nitrate, each one has 2 nitrogens. There's now a coefficient of 3. So that's a total of 6 additional nitrogens that are just staying as nitrate. So we need 6 more HNO3 to balance that. I'm writing it twice because nitrogen is changing its oxidation number as it goes from HNO3 to NO, but it's also staying the same in some cases as it goes from HNO3 to just this nitrate anion here. So I like to balance those separately because we treat them in different ways. We balance the first one here by using the number of electrons and making sure that they're both 6. We balance this one at the end by inspection. So we need 6 more nitrogens to keep the number of nitrogens balanced. You could just change the coefficient of 2 to an 8, but I think it's easier to keep track of this way. And then for water, what we have now are a total of 6 plus 18. We have 24 oxygens over here. Right now on the left side, we have 3 times 6 is 18 plus 2 is 20. So we need 4 more oxygens over here. I'm going to have to go through quickly because we're out of time. And then if we have 4 oxygens over there, that should take care of everything. So the final simplified version where we combine everything back together is 3 zincs, 2 plus 6 is 8 HNO3. So you don't have to separate it like this if you're kind of comfortable just keeping it all together, but you do have to make sure you add the correct number of nitric acids to ensure both that the number of electrons are balanced and that you don't lose any nitrogen atoms. So I ran out of room, but it's 38324, and that's the coefficient for HNO3, which with this asking would be an 8. All right, went a little bit over, so thank you for your patience, and I'll see you guys there.